All right, you guys, so we're going to talk about calorimetry next. So we've talked about internal energy and if you have different scenarios with heat and work and what that means for the total energy of a system. Calorimetry is just measuring heat. So we're just talking about Q. It's a process of measuring the amount of heat released or absorbed during a chemical reaction. It doesn't necessarily have to be a chemical reaction. It could also be just the addition of something hot to something cold and measuring that heat transfer from one to the other. But basically, we're measuring heat transfer. Coffee cup calorimetry is exactly what it sounds like. You use coffee cups and you put stuff in the coffee cups and you use a thermometer to measure a temperature change. You calculate Q, so you calculate the heat, based on changes in temperature at constant pressure, and it's constant pressure because it's just the atmospheric pressure. That's coffee cup calorimetry. Bomb calorimetry is much less exciting than it sounds. You're calculating the change in energy for a system at constant volume. So now you are putting your sample in a little chamber and you are essentially doing a combustion reaction, so making something explode in a small space, which pressure is obviously going to change, and you're measuring the heat given off by that combustion. That's bomb calorimetry. So they're very different setups, and they measure things a little bit differently, but you're essentially just measuring the heat that's given off by one thing and absorbed by another thing. Okay, so that is calorimetry. Here's a setup for coffee cup calorimetry. You have your thermometer and you have your, whatever you put in your cup, your reactants, your products, even hot water, cold water, which we're going to do in lab. Your solvent, we're going to use water, but you could use whatever you wanted. And then you layer styrofoam cups to insulate. The best ones are the Dunkin' Donuts cups, and they're really good insulators so that heat does not escape. When you have a discrepancy in your data, it's usually because at some point heat escaped and you didn't trap it all in your calorimeter. That's the setup for a coffee cup calorimeter. There are a couple constants that we need to talk about and equations that we use to calculate your Q, your heat, depending on the system. So first, heat capacity is big C. All right. It's a system's ability to absorb thermal energy without undergoing a large change in energy. So how much heat can something handle before its temperature increases? And it's dependent upon the amount of substance, which we call an extensive property, because it's dependent upon amount. Okay. So let's say you have a container and you need to figure out how much thermal energy it can absorb before you start to feel that container get hot. Okay, that's big C, and it's just depending on a temperature change. Remember, the delta T is going to always be final minus initial, and you calculate Q. That is mostly for bomb calorimetry, is when you use that. Specific heat, little c, or sometimes you'll see little c sub s, either one, is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree. So this is an intrinsic property, meaning that it's just something that is a characteristic of that material and it's never going to change. So everything, it's like a fingerprint, right? Everything has its own specific heat. It's defined the amount that you have. So let's say you go to the beach. Sand has a certain specific heat. Water has a certain specific heat. And so although the sun is the same and the energy given off by that sun is going to be the same at that beach, the sand and the water will heat up differently because of their specific heat. The sand could be super hot and the water can be really chilly, and it's just because of the specific heat of those two materials. Our equation, this one we're going to use all the time. M is mass. C is obviously specific heat. Your mass has to be in grams. Specific heat, you have your units of specific heat are joules per gram degrees C. And you can also have joules per gram Kelvin. Here it doesn't matter what your temperature units are in because you're just looking at the change. Either one works, and then Q is your heat in joules. Okay, the specific heat of water, this is a constant that we're going to use over and over and over again. 4.184 joules per gram degrees C. That's the specific heat of water. Okay, when you throw two reactants into a coffee cup calorimeter, you're going to measure whether that reaction requires heat. So your system will absorb heat from the surroundings, or released where your surroundings will get heat from your system, and we're going to do it in water. Delta H is your enthalpy, which is a measure of heat exchange at constant pressure. So basically it's the heat absorbed or released by a chemical reaction. So we're going to talk about enthalpy quite a bit. Essentially the difference between Q and enthalpy is that your enthalpy delta H is per mole of your reaction, whereas Q is just a general heat. Remember that endothermic is heat absorbed, so your sign is positive, just like it was with Q. Exothermic, heat released, your sign is negative, just like with Q. So we throw two things into water, let them react, measure the temperature change, and we calculate how much heat is absorbed or released. The thing that you want to remember is that your reaction, so let me just draw this out for you. All right, so here's my water. So here are my particles that are reacting. Okay, here's the party. So here's the reaction, RXN, reaction. Let's say that my reaction is exothermic, which means my reaction is releasing heat by the breaking and making of new bonds. Okay? What that means is that my water temperature is going to go up. It heats up my water because water is part of the surroundings. So my system is the reaction. Water is part of the surroundings, as is the beaker and everything else, but water. So what we measure is the temperature of the water, right? That's what we're measuring. So if the temperature of my water increases, that means that I have an exothermic reaction. If the water decreases, that means that my reaction has taken heat from the water and the water's temperature goes down because that energy has been stolen. So you have to change the sign when you calculate. So let's say you know the mass, you measure the mass of your reactants, okay? You are always going to use 4.184 when you do these reactions because that's water and that's the solvent that we're doing it in. We measure a temperature change. So we get an initial temperature and a final temperature and we subtract them, final minus initial, to get our change in temperature. And we calculate Q of my solution. Okay, so the solution will change temperature, but remember that we need to change the sign to get Q reaction because if the water temperature goes up, this is going to be positive because final minus initial will be a positive, but it's an exothermic reaction. So we got to remember to change the sign. Okay, don't forget to change the sign. If your water temperature goes down, you're going to calculate a Q that is negative because your temperature has gone down. But the solution is negative. The actual reaction, the system, is positive. So change the sign. Then what we need to do is calculate moles. We find Q, calculate moles, and we divide to get my enthalpy for the reaction because it's per mole because it's for a chemical reaction. My units are going to usually be given to you or expected for you to calculate in kilojoules per mole. So we are going to have to take Q and take joules to kilojoules and find moles in order to get the answer that you need. Okay. Let's do one. I'll show you how to do one. All right. So in this problem, you have 1.095 grams of NaOH and you are dissolving the NaOH. So this is we're making a solution of sodium hydroxide, which is a base. We're dissolving it in 150 grams of water. Please remember that if this told me that it was 150 milliliters, that is going to equal 150 grams because the density of water is 1 gram per mole. So if you get a volume of water, you can always just convert it 1 to grams because of the density. Anyways, we're giving grams, so who cares? So that's our mass. Initial temperature here, coffee cup calorimeter, final temperature here, and we want to calculate the heat and then find delta H. So first we're finding Q. We got to remember Q equals MC delta T. Then we have to find delta H, which is going to be the Q that we just found with a change in sign over moles. I'm just going to write down all the stuff that it told me. So that's my NaOH. And I dissolve in 150 milligrams of water. And my initial temperature is 23.5. And my final temperature is 25.32. Okay. This is the stuff that you're going to measure, the temperature. Okay, so we're just going to find Q first. And it's Q of my solution. So we're going to do MC delta T. My mass, I'm given 2 masses, and I'm adding these things up. I'm adding these things together in the coffee cup calorimeter. So I need to add up my masses. Okay, so I'm going to take from my mass, I'm going to do 150 grams. Plus 1.095 grams. Okay. I'm going to use the C for water because I'm doing this in water. And I told you can. And then I got to do my delta T. So I got to take TI minus TF. So I do 23.5 minus 25.32. Okay. My temperature has gone up, which means that my reaction has let off energy, has heated up the solution, which means that my actual reaction is exothermic. So I got to remember that Q is negative. Okay. Once you do all the math, you get a Q of solution is about 1151 with a little bit of rounding joules. So now that's my Q for my water, my solution. So for Q reaction, negative 1151 joules. Okay, there's Q. Now I have to find delta H. And in order to do that, I have to find moles. What we dissolved, what was actually doing the work, the water was just kind of hanging out. What was doing the work was the NaOH. So I need to use the molar mass, which I get from my periodic table. And if you need to review how to find molar mass, please do that. So I look at my periodic table and I find the mass for sodium, which is 23. And I find the mass for oxygen, which is 16. And I find the mass for hydrogen, and that's 1. And I add them up to get the molar mass of NaOH, which is 40 grams per mole. So I'm going to go ahead and find the moles right here. So I'm going to take 1.095 grams, and I use my conversion. My molar mass, when I add up all of Na plus O plus H, is 40 grams per mole. Grams goes on the bottom because I need whatever's up here to match whatever's down here, and 1 mole goes on the top because your units for molar mass are grams per mole. Grams cancel. So I take 1.095 divided by 40, and I get 0.027 moles. I'm going to take the moles that I just found with my Q, and now I can just find delta H. Okay, so I take 1151 joules, negative, don't forget, and I divide by 0.027 moles because that is what was doing the chemical reaction. And I get, this is going to be a big number and that's fine, 426 joules per mole. Remember I said it's usually in kilojoules, so we're just going to move that decimal place back 3. So I get about 42.6 kilojoules per mole. Don't forget that negative. I almost did. And that's your answer. We are going to use this for lab, so this is a good one to get used to doing. There's also a practice one like this in the homework. All right, so there's your answer. Here's number 12. I want you to pause. This involves writing and balancing an equation, which you should know for Gen Chem 1. So you can do your best with that. And go ahead and do part B. We're calculating the delta H of a reaction in kilojoules per mole. Remember what I said about density of water, so you're all good there. So go ahead and try that one. The answer. Check, make sure it makes sense. Now we're going to talk about, that was measuring the enthalpy of a reaction. Now we're just going to talk about throwing something hot into something cooler and figuring out what the various variables of that process are. So you can measure, if you don't know the specific heat of something, you can find it doing this method. You can determine what the final temperature should be. You can figure out what the mass is if you can't measure it or you don't know. So in these problems, heat is going to transfer from a hot object to a cold object or colder object. And we're always going to use water. Okay, so the equation that we're going to use is this one. Q metal is going to be equal to negative Q water. This is the way that it is notated in the book and in most books. Although the metal is the one that's losing the heat, it doesn't really matter, but they always notate that the water is the one negative. It doesn't really matter. I always get questions like, why is the metal the one that's positive if it's the one losing the heat? I don't have a good answer for that. It's just the way that they do it. That's the best I got. All right, so if you break this down, remember that Q equals MC delta T. So they each have their own MC delta T. So they each have their own mass. So we're not adding the mass here. They each have their own mass. They have their own specific heat. And they have their own temperature change. However, remember we talked about thermal equilibrium, where if you add two things that are different in temperature over time, they are eventually going to get to the same temperature. So although they have the same initial temperature, your final temperature for the metal, or whatever it is, and the water is going to be the same. So you will only get one final temperature, and that's okay, because they're both going to be the same. Let's look at number 13. So that's just this one. This slide's kind of busy. Let's just look at 13. So you have a 28.4 gram sample of an unknown metal heated to 110 degrees. So here's the mass of my metal. Its initial temperature is 110 degrees C. We put it into 100 grams of water. There's the mass of the water. And here's the initial temp of the water. Here's the final temp. Okay, and we want to calculate the specific heat of the metal. So here's how I like to solve these problems. I make a data table. Do you have to do this? No. Do I think it's a good idea? I do. Metal, water. We need mass, we need C, we need T initial, we need T final, and we need delta T. Remember, T final is going to be equal. All right, so we just pull the information that we need from the problem. So the mass of the the mass of the metal was 28.4 grams. My mass of the water is 100 grams. I don't know what the C for my metal is. That's what they're asking me. So that's my variable that I do not know. 4.184. I always know that for water. It's just a given. Initial temperature for the metal is really hot. Initial temperature for the water is room temp. And final temperature for both is 25.34 degrees C. Notice that the metal has this super drastic change in temperature, and the water goes up a little bit. The reason for that is that water has such a high specific heat. It's really hard to increase the temperature of water because of its high specific heat. It's pretty resistant to temperature changes. Whereas metals, as you may know, heat up super quickly, but they also cool down quickly. They tend to have a lot of thermal change. They can accept the energy quickly, whereas water doesn't. And that's one reason, although sand isn't metal, that's one reason why water at the beach stays cooler and the sand gets really hot, because water is pretty resistant to temperature change because of its high specific heat. Final minus initial is going to give us our delta T. So we subtract, and I'm going to get negative 84.66 degrees C. And here I'm getting 0.74 degrees C. Huge difference in temperature change. So remember, there's all the information that I need. And we're going to say Q equals MC delta T. And we also know that Q for the metal is negative Q for the water. So let's go ahead and plug those in. So you get MC delta T for metal is equal to negative MC delta T for the water. This negative sign is going to cancel out with that negative sign. So you're not going to get a negative number, but you need to have both of them there in order to cancel out. Okay, so let's plug in our values. I'm going to do this down here where I have more space. So I'm going to say, all right, 28.4 times C. My temperature change is my negative 84.66 equals negative 100 times 4.184 times 0.74. Okay, so I plugged all my stuff in from my table. This, and this. When I do this, I need to divide both sides by the variables that I don't know. So I'm going to take 28.4 times negative 84.66, and obviously that just cancels. And I'm going to divide this side by 28.4 times negative 84.66. Make sure if you put this into your calculator that you put the bottom in parentheses. Otherwise, it's going to divide by the 28.4 and then multiply that whole thing by negative 84.66. Just a little note for you. And we get 0.129 joules per gram degree C. And that is my specific heat of the metal. Just be careful to keep the water stuff with the water and the metal stuff with the metal. I want you guys to try 14, pause, and I will give you an answer. Here's the answer for number 14. Check your answer, make sure it makes sense. Now I want you to try number 15. 15, the math is a little bit trickier. It's not as straightforward, but I want you to give it a shot. Set it up, and then I will walk you through the algebra, because the algebra is a little bit trickier than it was previously. So try it, pause, and then you can come back and look at the answer. All right, so let's look at 15. You have to look up the C of aluminum. There's a table in your book, or you could Google it. It's pretty easy to find. But they don't give it to you in this problem. I might have given it to you on your worksheet, but either way, you might have to look it up. So I just tabulated all my stuff. So I got the masses, the specific heats, and the initial temperatures. I don't know what the final temperature is because that's what I'm finding. And since I don't know the final temperature, I don't know delta T. But I don't really care if I know delta T because I don't really need it. What I need is TF. So I set it up, MC delta T equals negative MC delta T. what I did was, since I don't know what delta T is, I just substituted in TF minus TI. TF is the same. So we only have one variable that we don't know. It's just in two places. We can solve that easy peasy. So what I'm going to do is I'm going to just plug in the values that I know, and I'm going to get kind of a big long equation here. So I'm going to say 32.5 grams times 0.903 TF minus TI is equal to 100 negative, don't forget that negative, 105.3 times 4.184 TF minus TI, sorry. What I'm going to do is I'm going to multiply these two values together to simplify, all right? So I'm going to take those two and I get 29.3 TF minus TI is equal to, and again, multiply those together and I get negative 440.6 TF minus TI. We know what TI is. I can just go ahead and plug that in. So I have 29.3 TF minus 45.8 equals negative 440.6 TF minus 15.4. Okay, I need to distribute this value into my parentheses. So I'm going to change TF to X just to like make my life easier. 29.3x minus, and then I do 29.3 times negative 45.8, and I get 1341.9 equals, again, I take negative 440, I'm going to call TFX, and then I multiply those together. This sign is going to change to plus because you have two negatives there, 6785. 0.24. Okay, now we combine like terms. So I'm going to add 440.6x to this side. Right, and that's going to cancel that out. I'm going to add 1341.9 to this side. So what I end up with is 469.9x is equal to 8127.14, which is like a lot of sig figs, but, and then you divide, get x by itself, 17.3 degrees C. It is not impossible, it's just a little bit more work than the other ones. So what you want to make sure when you check your answer here, and your book does it a little bit differently, so in the mastering video you can see how they do it, and if you like their method better, do it their way. You want to make sure that your temperature is in between these two. Your answer should not be outside of your initial temperatures. There's no way that you're going to get lower than 15.4 or higher than 45.8, and you're going to be closer to the water temperature. So there you have it. So that's a way to check your answer. If you do get outside, then something happened with your math. That is the end of the work you're responsible for week 1. The quiz will be on something that we have gone over. Do the homework. If you have questions, bring them to class. I'll see you next week.